Assalamualaikum and greeting to Dr. Izzharif. My name is Mohamed Aiman bin Hamzah, and along with my team members Hanis, Mardhiah, Binti, Affendi and Putri, Balqis, Binti, Rashid, we are presenting on the topic of forensic analysis of cigarette ash using handheld X-ray fluorescence for subject FRS651 forensic chemical analysis. Forensic science is an essential field in criminal investigation, playing a crucial role in linking evidence to suspect and crime scene. One of the key aspects of forensic science is the analysis of trace evidence, which includes minute samples such as fiber, hair, and in our case, cigarette ash. Though often overlooked, trace evidence can provide vital clues that help reconstruct events leading to a crime, as well as identify perpetrators. Cigarette ash, in particular, has significant forensic value. This seemingly trivial substance can be found at crime scene and can be used to link a suspect to a particular location or activity. For example, the criminal composition of cigarette ash can help identify the brand of the cigarette smoke, the presence of the specific contaminant or substance, and even the geographic origin of the cigarette, all which are available in crime scene reconstruction and suspect identification. Cigarettes can be particularly useful in crime scene reconstruction, as its chemical fingerprint may point to specific brands or even specific batches of cigarettes. By analyzing the elemental composition of the cigarette ash, forensic experts can gather crucial information about the environment and the people involved in a crime. In some cases, cigarette ash may even serve as the only link between a suspect and the crime scene, making its analysis indispensable. Now, the question arises, how do we analyze cigarette ash efficiently and accurately? One method gaining prominence in forensic science is X-ray fluorescence spectrometry. This technique is particularly suitable for analyzing cigarette ash due to its ability to provide rapid, non-destructive elemental analysis of the sample. Handheld X-ray fluorescence spectrometers in particular allow forensic experts to conduct real-time analysis on-site without the need for transporting samples into a lab. This portability and immediacy makes X-ray fluorescence an invaluable tool in criminal investigation, allowing experts to make informed decisions quickly during the course of an investigation. In this presentation, we will explore the application of handheld X-ray fluorescence spectrometers in the forensic analysis of cigarette ash, focusing on how this tool enhances the ability to extract meaningful information for what may seem like a small, inconsequential piece of the evidence.
Hi, my name is Putri Balqis, and now I will continue the presentation by presenting the principles of the handheld X-ray fluorescence. So, for the principle, you can divide it into three parts, which first is the non-destructive technique that apply to this instrument, which the samples that we found at the crime scene or place can be analyzed directly without damaging the samples. Example for these studies are the cigarette ash. So second is the in situ analysis, which means that the sample can be directly analyzed at the crime scene or on site. And the third principle is the X-ray emission, which it analyzes the fluorescent X-ray that emitted when a sample activated by the X-ray main source. To the advantages of the handheld X-ray fluorescence. So first one is it portable and convenient instrument, which is perfect to the on-site forensic analysis because it particularly for materials that are very highly sensitive. And, for this study is the cigarette ash. So the ability of this instrument is to analyze the small amounts of materials or samples. So this because the size of the instrument is like small benchtop centrifuge, so it's very compact and easy to bring to the crime scene for analyzation. So second is the cost effective. So it shows the reduce of the necessity for large laboratory sets. So the third advantage is the rapid and accurate analysis. So it shows the fast and highly accurate for multi-element data because this method involves a quick, simple and inexpensive laboratory base for sample preparation procedure. So the last part for principle of handheld X-ray fluorescence is the limitation itself. So the limitation can be divided into three, which is first is the limited detection range, which is for achieving consistent result, often require longer analysis durations. So sometimes up to 7 minutes for lower concentration. So it shows that this instrument can be less successful at finding element in extremely low concentration. So the second limitation is the metric effects. So basically secret ash can vary significantly in composition depending to the brand or type of tobacco used. So this variability can affect the signal from the analyzer and can lead to the inconsistent result. So the accuracy can be influenced by the chemical composition and also the sample's physical. So the third limitation is the low sensitivity for the trace element. As you know, in cigarette ash itself, there are few type of trace elements such as potassium, magnesium, and copper. So when we use this instrument, it prioritizes the larger compound or larger component that not including some essential light components because heavy metal we can detect it by the analyzer at least at 10 ppm at low concentration because when we achieving the similar sensitivity or less abundant from the trace element, so it gives more difficulty to analyze the samples if we use this instrument.
The handheld X-ray fluorescence analysis helps identify the elements found in cigarette ashes originate from various parts of the cigarette. Firstly, tobacco leaves. The tobacco plant absorbs elements from the soil including iron, cadmium, potassium, magnesium and copper. These elements are concentrated in the tobacco leaves and are present in the ash after combustion. Secondly, cigarette paper and filters. Some elements like calcium and potassium can also be present in the cigarette paper and filters, contributing to the overall elemental composition of the ash. Thirdly, combustion products. During combustion, elements from the tobacco and paper are released and concentrated in the ash. This includes sulfur, phosphorus, and zinc, which are present in the tobacco and become part of the ash. Finally, environmental contamination. Trace elements such as lead, cadmium, and arsenic can be absorbed by the tobacco plant from contaminated soil or air pollution and end up in the ash. Handheld X-ray fluorescence operates on the principle of X-ray fluorescence, where a sample is irradiated with X-ray, causing the atoms in the sample to emit characteristic X-ray. The energy of this emitted X-ray is unique to each element, allowing for its identification and quantification. The table presents the elemental X-ray emission data of the elements found in cigarette ashes. The handheld X-ray fluorescence can differentiate tobacco brands by analyzing the elemental composition of cigarette ash. Each tobacco brand may have unique elemental profiles due to factors such as cultivation methods, soil composition, fertilizers, and additives. Firstly, elemental fingerprint analysis. Each cigarette brand contains a distinct combination and concentration of elements such as zinc, copper, aluminium, cadmium, which it generates an elemental fingerprint by detecting and quantifying the unique presence of these elements, helping to distinguish brands. Secondly, comparative concentration profiles. Major elements such as cadmium and ferrum and trace elements such as copper and zinc show variability across different brands due to differences in tobacco sources and manufacturing processes. Statistical analysis of elemental concentration using percentage or ppm can highlight distinct patterns for each brand. Thirdly, geographical tracing. Elements like chlorine, ferrum reflect the soil and water condition where the tobacco was grown. This analysis helps link cigarette ashes to specific geographical regions based on elemental content which varies with soil pH, climate, and fertilizer use. Furthermore, additives and manufacturing differences. Some brands use additives such as flavoring agents or combustion regulator such as phosphorus, sulfur, and heavy metals, which these can identify these additives, which may serve as unique marker for specific brand. The fifth one, the multivariate data analysis. By applying principal component analysis or cluster analysis, the elemental data from different secret brands can be grouped based on similarities and differences, providing a clear distinction between brands. This approach enhances discrimination based on subtle differences in elemental composition. The sixth one, elemental ratio. Comparing ratios such as potassium with calcium, ferron with aluminium, or copper with zinc provides a brand-specific signatures that can be used to categorize different secret brands. And finally, detection of contamination. Some brands may contain contaminant such as plumbum, cadmium, or arsenic due to poor quality control or environmental exposure. It can detect these toxic elements, which can serve as differentiating factors. This application uses two statistical methods. Firstly, one-way ANOVA with Turkey post hoc test. One-way ANOVA is used when you want to compare the means of 3 or more groups, in this case, different secret brands, to see if there are significant difference in the average elemental concentration, such as potassium with calcium, between them, and Turkey post hoc test is performed to determine which specific brands differ from each other. This test compares all possible pairs of brands to see if the differences in their mean concentration are statistically significant. On the table shown below, the ANOVA test shows that the p-value with 0.02, which is less than 0.05, this means that there are a significant difference in the potassium concentration between the brands. Then, the Turkey test results then performed to identify which pair of brands are significantly different. On the table show, in conclusion, brand A and B, B and D, C and E have significantly different potassium concentration, while brand A and C and other pairs do not differ significantly. So, the summary of how the two tests work together, one-way ANOVA, it tells us whether there are overall differences between the secret brands in terms of their elemental concentration, while Turkey test, then if ANOVA show a significant result, Turkey test tells us exactly which brands differ from each other.
To summarize this, handheld SRS spectrometer has proven to be an effective forensic tool for the rapid and non-destructive analysis of cigarette ash. This technology is essential for on-site, real-time analysis in forensic investigation, providing valuable data quickly at crime scene. Looking ahead, there are promising future prospects for SRF in forensic science, such as improving the accuracy of elemental analysis and expanding forensic database to cover a wider range of applications. Finally, the practical use of SRF in forensic investigation, particularly in crime scene analysis and law enforcement, shows how versatile and effective it can be in helping to solve criminal cases. This to enable quick, reliable decision and real-time, enhancing the criminal justice processes. That's all for us. Thank you.